All right, last problem from this set, number 8. We have a ball given mass, and it's moving pretty quickly when it's 3 meters above the ground. Now that's pretty fast, and that's not very high. So kind of reading into this, it was originally dropped from a considerably higher height of 100 meters, and the question is how much energy was lost to air resistance during its fall. Now, of course, air resistance is something that we default to assuming is not present in our problems. That's going to continue to be the case by default. However, of course, a question can change that on us by explicitly saying something to the contrary. So in this question, there is air resistance. And air resistance can be a very complicated thing, but in this question, I think it's going to fit in rather simply. So here we go. Ball has a mass of 0.35 kilograms. It's moving at 40 meters per second. Now, I'm thinking of this as like the later stage here. So I'm going to call that V prime of 40 meters per second when it is at that later stage at a height of 3 meters above the ground. We're measuring height from the ground. Hopefully that's clear. It was originally dropped. So this is that starting condition. It was originally dropped from a height of 100 meters. And again, that word drop tells me that it had that starting velocity of 0. It wasn't thrown. How much energy was lost to air resistance during its fall? Well, that's the net work done by non-conservative forces. As the ball falls down, the air resistance force would be acting upwards on it, opposing that motion. And with that upward force and that downward motion, the force of air resistance would do negative work, basically removing energy. And since it's the only thing doing that, I'm gonna basically equate that with the net work done by non-conservative forces. The air resistance is the one and only force that is doing work in this way. So the ending energy is equal to starting energy plus the net work done by, in this case, air resistance. But I'll keep that generic label on it. K prime plus U gravity prime. This very quickly becomes routine, equal to K plus U gravity plus the net work done by non-conservative forces. Let's cross out the things that we know are 0. Actually, in this case, there's not much. It started from rest, but the height was not 0 in either case, so I'm going to keep both of my U gravities. K prime, it's moving quickly, and of course, the net work non-conservative is the thing that I'm looking for. It's definitely not 0. Okay, so if you want to know the net work done by non-conservative forces, why don't we just solve for that right now? Network NC is equal to K prime plus U gravity prime, and I'd have to subtract the U gravity to join those terms. That means that the net work done by non-conservative forces is 1/2 mv prime squared plus mgh prime minus mgh to start with. And we know all of those things on the right side of the equation, so this is really just a matter of plugging them in. 1/2 m, which was, I have to scroll, 0.35, 0.35, and it was moving at a v prime of 40, so squared, plus our 0.35 kilograms again, 9.8, the h prime, it was what, 3 meters, I think? Yeah, 3, and then minus 0.35 kilograms, 9.8, starting at 100 meters. So squeezing that in there, I got it. And it's calculator time. So just grab a calculator, 0.5 times 0.35, 40, don't forget to square that, plus 0.35 times 9.8 times 3, minus 0.35, 9.8 times 100. And hopefully I didn't mess that up. I'm getting negative 52. And just 3 figures is enough, so I'll call it 52.7 joules. And again, the reason that's negative makes sense. The air resistance would take away mechanical energy. Think of it this way. If not for air resistance, it would have had an extra 52.7 joules, and it would have been going even faster than the speed that we know that it had here of 40 meters per second. That is a considerable fall. So without air resistance, it would have been going even faster, but air resistance robbed this ball of 52.7 joules in its fall by doing negative work to it. And that's the end of the worksheet.